I'm very happy to be here again in Marseille and to present you this recent work with Ionikita and Kurchet Fitter. So I want to say that this work started at the end of my PhD, and now it's finished. So you can have a look at it at the archive. So I give the references at the end. So I will talk a little bit about random tensor networks with the new approach, which is with the maximal flow approach. And in this talk, it will be related to some random matrix theory and free probability theory also. And we will see how all these topics comes together to understand some properties, some quantum information properties of these random tensor networks. And by the way, for this talk, I will not give almost any proofs. So it's the end of, so it's the last talk, so it will be a little bit relaxing. So maybe I will just, I will give some example, and I will derive the explicit formulas for in that example. Okay. So here is the here are the topics that So we will start with the say basic definitions of random tensor networks, and then I will tell you a little bit what is this maximal flow approach and what it allows you to do, and I will end up with the main results and with the conclusion. So let's start. So what is random tensor network? So we heard a little bit about it in Angela's talk. So random tensor networks, or tensor networks in general, also it appears in different contexts. So in physics, in condensed matter, in quantum gravity, people who are interested on these topics. And the random tensor networks start initially to understand, I would say, some entanglement properties of some models, which is motivated, I would say, as toy models to understand some quantum gravity phenomena. So I will not go into that direction unless if there is some questions at the end of the talk. So basically, for me, what is a random tensor network? So you have a graph, and from this graph, so you have two regions. I don't know if, no, we don't see. Okay, that doesn't work. Okay, so you have a graph structure, and in this graph, so you have edges and you have open edges, and you will construct from this graph. So this graph structure is completely fixed. And you will construct from it some random tensor network. So you will define some random quantum state from this graph. And what you are interested in is to understand if you separate one region from the rest. So you will trace out the other degrees of freedom, or you will trace out the other parts that you are not interested in. And you want to evaluate the average of entanglement entropy, von Neumann or Rényi entropy, and you want to take the limit as d goes to infinity. And the main goal of this talk is to show that this quantity here scales like log d times something, so that will be precise later in the talk, plus some higher order correction terms, which have actually some physical interpretation. Okay. So now let's be precise. So what is a random tensor network? So as I said, so you have graph, and in this graph you have bulk. You have bulk edges, so you have just edges. So bulk edges, for me, I call them just edges. So, and you have boundary edges, which are the open edges. So for example, here, so you have these open edges right here and right here. And inside you have some bulk, you have some edges that connect two vertices. And for each boundary edge, so I will denote by x dot, so the boundary edge, I will associate complex vector space finite dimension D, and for each edge, so I will associate two copies of CD, and I will define some states, maximally entangled state that will connect the two vertices in my graph, and for each vertex of my graph, so I will look at all the Hilbert spaces that will contribute to the vertex, to the vertex. So I will have half edges that will contribute, and I will have also edges that will contribute, and this will give me a local Hilbert space that is induced by the open edges and the edges of my graph. And I will define on each vertex, I will define some random Gaussian tensor. Okay, so this is the model. And now, what is a random tensor network? So a random tensor network, so you will take actually all the vertices. So you will take all the vertices of your graph and random Gaussian states defined on each vertex, and you will project it to the maximally entangled state. And you can check that this state, this random tensor network, actually lives in the boundary region or in the half edges of your graph. So for example, in this example, so you have this state, it lives actually in CD tensor 10, so we have 10 open edges. So it's basically, it lives in CD tensor 10. Okay, I don't know if there is some question right now, or should I continue? Okay. So the first computation that we will address is to take some subregion A. So this is in orange here, my subregion A. I want to compute the moment of trace of row A to the power n. Okay. Here, oh no, this one or this one? This one. Okay, perfect. Check. So how do you compute this? So this is well known. So first you will look at. So let's take n first is equals to 2. So you will have. So the expected of trace of row A square, and this is equal to the expectation. So here the average is of a random Gaussian state. So it's trace of my random tensor network over 2 copies of my random tensor network contracted with, I will call it a flip operator. So what is this flip operator? It's basically the tensor product over all half edges that you want to flip in order to have this to obtain your state row A, and you will act with the flip operator in each half edges. So what is this flip? So this flip operator acts in this way. And if you apply it twice, so you can check that this is just identity over D, so if you are working in D-dimensional. And the trace of a flip operator, it is equals to D. And so you do it, and after, so you will extract, so remember, so you have, you will expand a little bit the expression right there. So it will be, so you will have maximally entangled state, and you will have your Gaussian state, random Gaussian tensors defined for each vertex, and you will have your flip operator. And when you take the average, so average by linearity, so it's just go here, and then you will apply Wick's theorem. So here you will apply Wick's theorem, and you will, and at the end, so you will have something d to some powers. When you put everything together, so you will have d to some power to some power. So either you will have d to some power d squared, etc. So it will depend as power of the dimension, and in general you can show that this can be generalized when you look at trace of row A to the power n. You will write it as trace of psi j over n copies tensor n, and now you, instead of you have the flip operator, so you will have the full cycle A that will act, and again, so you will apply Wick's theorem, and you will have different contribution of d to the number of cycle of different permutations that you will apply. And the number of cycles, as we have, is related to the Cayley distance. So by alpha x minus 1, alpha y is n minus the number of cycles between two permutation elements. And when you plug these formulas right here at the end, so we will have something d to some powers that will contribute, and you will have different constraints. So the permutation element that appears in the region A will be constrained to be equal to the full cycle. The complementary region, so which is B, so for me B, it's so sorry, so maybe I did not mention it, but B is just E boundary. So it's the complementary region of A, and in the bulk, so we will have competition between different permutation elements. So I don't know if it's clear, but you will have different contribution of d to some powers that will depend on the different permutations that you will choose that will appear actually when you compute the moments and with the weak theorem. Okay, so now what is this? So I will start with the maximal flow approach, and what I will tell you a little bit what it allows you to do. So first, you have your original graph, and you will construct, and from your original graph, so you will construct a network. So what is this network? So I think I need to use it again. Okay, sorry, I did not expect that, but okay, so what is this network? Okay, up. So you have, as I said in the beginning, so you have a graph, and you have open edges, like this, and you have the region, and you have the region A, you have the region B, and you have your region A. And from this graph, so you will construct a network. So I will call this, it's GAB. So we will connect all the half edges in B to the to identity, and you will connect all the half edges in A to the full cycle. And this I call it the network. And the difference between these two graphs is that in this new graph, the vertices are valued in the permutation group. Okay. So this is the your network. And now what is the maximal flow? So the maximal flow will consist on looking at actually the different edge disjoint paths that will start from identity and will go to gamma. So the identity I will call it the source, and gamma I will call it the sink. So we will have different paths, and you need to look at the maximal number of edge disjoint paths in your graph. So this is the definition of the maximal flow. So here is an example. So as I said, so we have our favorite graph, and you have the region B, and you have the region A, and you construct this network. So this network, you attach identity to the region B, and you attach to the region A the full cycle, and you want to see to look at the different paths that will start from identity and goes to gamma. So here is the four paths actually, which are the maximal here, and you can check that if you remove these four paths here, so you can fully disconnect identity and gamma, and this and each path actually will induce an ordering that will appear later. So this is the maximal flow. So the maximal flow that you can achieve in this network is equals to 4. Okay. So there is a famous theorem due to Menger. So Menger's theorem tells you that if you know what is the maximal flow on your graph, so you know the number of minimal cuts. So the minimal cuts, it's the minimum number of edges that you need to remove in such a way that you disconnect completely the source and the sink. So for example, so again, our example, so this is the maximal flow that you obtain in your network. And here is the number of cuts. So here you have the minimal cuts. So you see you need to cross four edges. And you see if you follow these cuts, for example here, you fully disconnect completely the source and the sink. So the identity and gamma. And here you can see that you have other other minimal cut that can intersect, that can do whatever. So it depends really on the graph on the network. So this is kind of duality between between the maximal flow and the number of minimal cuts. Okay, so again, with this example, so we have our maximal flow. So we have the four paths that achieve the maximal flow in different colors, and you see if I remove this four paths, I can fully disconnect completely the identity from the full cycle, and here I will call it the residual network. And what this residual network? So you will the remaining permutation elements which are connected. So I will take them as a single pair. I will consider them as a cluster of permutations, and there is a partial order that you can construct, because you have, you remember that in the maximal flow, so you will have an ordering, and this partial order, it tells you how these elements can be related in an order way. And here, each vertex in this partial order actually are the cluster of different permutation elements. Okay. So the first theorem that you can show, is that you take the average. So you take the moment. You have the moment convergence of trace of d to of trace of d to the power maximal flow minus the number of number of half edges in your graph. So this quantity converges to a graph to the moment of a graph dependent measure that will depend on your network. And in particular, actually, if you obtain the partial order is series parallel, so you can know explicitly. So I can give you a formula. So I can explicitly give you the measure associate to this network. So you see here the partial order that I define that arise actually from the maximal flow approach, etc. that you have. So it's a series parallel network. So I can completely give a measure associate to this partial order. So now I need to tell you what is this partial order, and I need to tell you what is this notion of series parallel and how you can and how you obtain these measures. So I will go a little bit into the main result. I don't know if there are some questions so far or something you want to come back to. No? Okay. So what is this series parallel? This series parallel network. So you take two directed graph. So you have a source And from this source, so it can you have your directed graph. So you have a source and you have a sink. So in H1 you have source one and you have the sink, and from this graph, from this directed graph, so you can combine in series the two graphs. So you have, let's say you have H1 and you have H2 with different source and different sink. So the series composition consists on identifying the sink of the first with the source of the second, and you can construct a new directed graph. And the parallel concatenation consists of identifying now the source of the first of the first directed graph with the source of the second one, and the sink with the sink, and you obtain this partial order. And if your directed graph can be constructed just from these two operations, so we say that this graph is series parallel. So now we will define, so for a series parallel graph, so you will associate some measures. So for a trivial graph, so which consists only on vertex connected with an edge, so you will associate a Dirac mass. And if your graph now is constructed from a series concatenation, so you will associate a measure to your first graph with a free product convolution with the Manchesco-Pastor distribution, and free product convolution with the second measure associated to the second graph. And if it's parallel, so it's classical product. And the Manchesco-Pastor distribution was introduced today, and I don't know if the free product convolution will be also introduced, but you can think of it like in classical probability theory, like a standard convolution that appears in free probability theory. Okay, so now with these definitions, so let me come back to our network. So we have this partial order, and you see we obtain from, remember that this partial order is obtained from the maximal flow, and the maximal flow will induce an ordering in your graph, and when you take off all the paths, so you will have this clustering operation that will allow you to construct this partial order. And you see, so let's see if this graph, this partial order, is series parallel. So you can see that you can rewrite it as composition of series with this first graph, in composition in series with the second one, and in composition of series with the third one. So, and if you zoom in if you zoom in the graph G1, so you can see that it's parallel with G4 and G5. So you identify the source of G5 with the source of G4, and the sink of G4 and the sink of G5 with the sink of G4. And now, if you zoom again in the graph G4, so you can see that it is given by, you see that it's G6 in parallel with the G7. So you identify again the source and the sink of G6 and G7, and in series with the graph, G8. And again, for the graph G5, so you see that you have G9 in series with G10 and in series with G11, which is parallel with G12, and everything is in series with G13. So you have this composition of series parallel, and you can, and then this partial order is series parallel. So now let me come back. So let me come back to the previous definition. So I've told you that if you have so if the graph is trivial, so you will associate trivial, sorry. So you will associate a Dirac mass, and if it's and if the graph is given with series composition between the two, so you will associate a measure. So you associate the measure of the first graph, free product convolution with Machesko-Pastur, free product convolution with the second graph, and if it's parallel, so you will associate the normal the product of the two measures. So you see here. So let's apply this for the first one. So you see mu of G0 AB. So you will obtain mu G1 free product convolution with free product convolution with Machesko-Pastur, free product convolution with delta 1, free product convolution with Machesko-Pastur again, free product convolution with delta 1. And this, it will give you mu G1 free product convolution with Machesko-Pastur twice, so as a free product convolution. And then you will do the same operation for the different other graphs. So mu G1, if you repeat again the operation, so it's just mu G4 times mu G5, and again you iterate, and you can and again you iterate like in the example that I give here. And when you do so you have mu G1 free product convolution with Machesko-Pastur twice, mu G2, so this is the classical. So mu G4, so you can see that that gives you Machesko-Pastur classical twice with the free product convolution with Machesko-Pastur. And again mu G5, so you can check with the same operations that it gives you Machesko-Pastur free product convolution 3 times this time, free product convolution with the Machesko-Pastur free product convolution twice with classical Machesko-Pastur. So you see now, so this full partial order that you have obtained, so is series parallel, and this is the measure that I can explicitly give you when the partial order is series parallel, and it mixes between free product convolution and classical product. Okay, so this is the main theorem. So you can show that if you compute the Renyi entropy or the von Neumann entropy, and you take the average and you take the limit as d goes to infinity, so it scales like log d times the maximal flow or the minimal cut with some correction terms which are graph dependent. And if the partial order that you obtain from your maximal flow, etc., is series parallel, so this we can explicitly give you this measure. So to prove this theorem, so you need to prove some concentration inequalities, and you need to work a little bit, but with standard probabilistic argument. But it's not. So the main idea is if the partial order is series parallel, so we can give you actually explicitly the measure that the measure with free product convolution and the classical product of Machesko-Pastur distribution. Okay, so to conclude, so here is the take-home message again. So here with the maximal flow, we were allowed to compute the average Renyi entropy or von Neumann entropy as d goes to infinity. So it scales like log d times the maximal flow or the minimal cut plus some higher order correction term which are graph dependent. And if with this, and by the way, we did not assume any assumptions on the minimal cuts. So you can have different minimal cuts that can appear in your graph when you analyze with the maximal flow. And the higher order correction terms are graph dependent. And if the partial order is series parallel, so you can explicitly give the measure associated to the random the measure associated to the network. Okay, so for those of you who are interested on those topics, so there's a nice reference on tensor networks. So tensor networks are a very, very huge field that intersects between condensed matter, high energy physics, quantum gravity, and quantum error correction. So there is a lot of things that I could not say. So I really invite you, if you are interested in such topics, to look at this to this nice reference. Also, the link with quantum gravity and quantum information theory. So actually, the random tensor network models appears as toy models of some quantum gravity. If you heard about ADS-CFT correspondence. So this is a nice reference also where you can when you can see the link between quantum information theory and the link with quantum gravity, and now also with free probability theory. Also, so this is the first paper that shows that introduces actually the random tensor networks in the context of quantum gravity, but also random tensor networks start to appear nowadays almost everywhere. So also in condensed matter or in random quantum circuits, etc. So there is a very exciting things going on. And the first paper that gives the link, as far as we know, that gives the link between random tensor networks, holography, and free probability theory. So it's this one that inspires us a lot for this work, and I think it will inspires us for a couple for a couple of I would say of years. And if you are interested to know more about the maximal flow approach, I invite you to look at our new paper uploaded recently in the archive. And I would like to thank again Koshet Fitter and Ion Nikita for this project, and I would like to thank you for your attention. And if there is any questions, I would be very happy to answer. Thank you very much.